All right, let's talk about IV bags. We've all seen them hanging next to a hospital bed, that clear bag of fluid just dripping away. But have you ever really thought about what's inside? Because, let me tell you, it is way more interesting than just a bag of water. Today, we are going to go inside the IV bag and really understand what makes these things tick.
Right? You see these names printed on the side: normal saline, lactated ringers, D5W. And it's like, what's the difference? Why do we need so many options? Well, that is the big question we're going to tackle. Choosing the right fluid isn't just a minor detail. It's a super critical medical decision, and you're about to find out why.
So here's how we're going to break it all down. First, we'll cover why this even matters in the first place. Then, we'll take a quick tour of your body's plumbing, where all the water goes. After that, we'll get into the two main families of IV fluids, then do a deep dive into the ones you see most often. And we'll wrap up with a few special cases and the big takeaways. Ready? Let's go.
So think about it this way. For your body to run smoothly, especially when it's under stress from an illness or injury, its internal chemistry has to be in perfect balance. And that's really what this is all about. An IV fluid isn't just a drink for somebody who can't sip from a straw. It's a precision tool for fine-tuning that incredibly delicate balance. And it all starts with this one number: 60%. That is roughly how much of your body is made of water. But, and this is a huge but, it's not like you're just a big water balloon. That water is meticulously organized into different compartments. And understanding where that water lives is the absolute key to understanding how these IV fluids do their job. Okay, so if the water is split up into all these different compartments, what does that map actually look like? Let's take a look at the body's internal waterways, because where a doctor wants that IV fluid to end up, well, it all depends on navigating this map perfectly.
And here's the first big split. And honestly, this might surprise you. A full 2/3 of all the water in your body is intracellular. That means it's actually locked away inside your trillions and trillions of cells. Everything else, all the fluid in your blood, between your tissues, that only makes up the last third. Now let's zoom in on that last third, the extracellular fluid. Even that is divided into two really important spaces. The vast majority of it is what we call interstitial fluid. That's the stuff that's just kind of bathing the outside of all your cells. The much smaller part is your plasma, which is the liquid component of the blood inside your veins and arteries. This difference is going to be so important in just a minute.
So, how does water know where to go? It all boils down to this one kind of sci-fi sounding word: osmolality. But the concept is actually super simple. Think of it like this. Water is lazy. It always moves from an area that's less crowded with particles to an area that's more crowded, just to even things out. Osmolality is just the measure of how crowded a fluid is. Your blood has a very specific crowd level, right around 290. And IV fluids are designed to either match that, be less crowded, or be more crowded. And that's how we can force water to move exactly where we need it to go.
Okay, with that groundwork laid, we can finally talk about the fluids themselves. And at the highest level, they all fall into one of two big families: crystalloids and colloids. Now, the difference between them is really simple, but it has absolutely massive consequences for how they work in the body.
It really is all about size. Crystalloids are made of teeny tiny particles, things like salt and electrolytes. They're so small they can easily leak right out of the blood vessels into that interstitial space we talked about. But colloids? No way! They're made of big, bulky molecules like proteins. They're like the bouncers at a nightclub. They are too big to get through the door of the blood vessel, so they stay inside and they hold all the water inside with them. That's why they're called plasma expanders. They literally expand the volume of fluid inside your bloodstream.
Since crystalloids are by far the most common type of fluid you'll see, let's take a closer look at them. These are the everyday workhorses of medicine, but they are not all created equal. They get broken down into subcategories based on that concept we just mastered, osmolarity.
First up, we have isotonic fluids. Iso just means the same, so their concentration, their crowd level, is a perfect match for your blood. And because it's so balanced, giving an isotonic fluid is like topping off a tank without changing the mixture. It's not going to cause a big shift of water into or out of your cells. This makes it the go-to choice for general dehydration or to replace lost blood volume.
Then you've got the hypotonic fluids. Hypo means less, so these fluids are way more diluted than what's inside your cells. So what does our lazy water do? It sees the more crowded party going on inside the cells, and it rushes in to join, plumping those cells up. And this is exactly what you'd want if a patient's cells themselves are dehydrated, like in a condition called diabetic ketoacidosis.
And finally, there are hypertonic fluids. Hyper means more. These are super concentrated, think salt water. Now, when you introduce this into the bloodstream, it suddenly makes the area outside the cells way more crowded. So what happens? Water gets yanked out of the cells to try and dilute it. This is an incredibly powerful, almost an emergency-level tool. For instance, if a patient has dangerous swelling in their brain, a hypertonic solution can literally pull that excess water right out of the brain cells and potentially save their life. But even within the isotonic family, not all fluids are created equal. Just take a look at this table. On the far left, you see the normal composition of our own blood plasma. Now, compare that to maybe the most famous IV fluid of all time, 0.9% normal saline. Check out its chloride level, 154. That is way higher than our body's natural level. This is exactly why it's called an unbalanced solution. Now look over at lactated ringers or Plasmolite. See how much closer their numbers are to our own plasma? That's what makes them balanced.
And you know, this imbalance isn't just academic. It has real consequences. Just as this quote points out, if you give someone huge amounts of normal saline, you can actually overwhelm their body's ability to deal with all that extra chloride. It can lead to a condition called hyperchloremic metabolic acidosis. And this is a huge reason why you see a lot of hospitals moving away from saline and towards those more balanced fluids.
All right, we have covered a ton of ground. Now that we've got the fundamentals down, let's just look at a couple of weird, special cases and then tie it all together with the most important things to remember.
Okay, check out this chameleon of a fluid. It's called D5W, which is just 5% dextrose, or sugar, in water. Now in the bag, if you measure it, it's technically isotonic. But here's the trick. The second it gets into your body, your cells immediately gobble up all that yummy dextrose for energy. So what's left behind? Just plain old free water. So its actual effect on the body is hypotonic. It's a two-step fluid, a real transformer.
And let's just quickly revisit those big molecule fluids, the colloids. Remember albumin, our plasma expander? Its whole job is to stay in the blood vessels and hold water there to crank up blood pressure. But this comes with a huge risk. In conditions like a bad infection or sepsis, the blood vessels can get really leaky, kind of like a garden hose filled with holes. And if those big albumin molecules escape through the holes, they act like little sponges, pulling massive amounts of water into the tissues and making a really bad situation, well, catastrophic.
So if you remember one thing from all of this, let it be this. An IV fluid is a prescription drug. It is not just fancy water. Every single one of these bags is a precision tool designed with one very specific mission: to move water from one compartment of the body to another, all in the service of restoring that delicate, life-sustaining balance.
In the end, that simple-looking plastic bag of clear fluid is one of the most powerful tools we have for manipulating human physiology. The real art and science of medicine isn't just knowing that they exist, but knowing exactly which patient with which problem needs which fluid. It's all about choosing the right tool for the right mission.